Okay, hello, ladies and gentlemen, and welcome to another discussion on chemical concepts here. Today, we're going to start with Chapter 18, and we're actually getting to the end of the school year, so we've only got a couple chapters to go, Chapter 18, Chapter 19. We actually only have a couple weeks to go. And what we're going to do is this week, we're going to cover sections 18.1 and 18.2. And then next week, we're going to have one assignment on sections 19.1, 2, and 3. The reason we're covering it that way, and I'm going to take into account that we're going to be throwing a lot of sections at you, is because, these are actually two pretty important concepts in chemistry. Chemical equilibrium, and Chapter 19 is on acids and bases. And, what good chemistry class doesn't talk about chemical equilibrium and acids and bases? But unfortunately, we're up against it. We're at the end of the school year, and, we're not going to have, we've run out of time. So I at least want you guys to kind of at least be exposed to what chemical equilibrium is and what acids and bases are. And I'll take into account how many questions I ask you, especially with the acids and bases. I may ask questions I ask you to do for the assignment. And I'll take into account, how difficult the questions are going to be on the quiz, because they can be pretty difficult. I mean, these two sections can cover at least 5 to 6 weeks of a college chemistry class. And we're going to do those two sections in 2 weeks. And they can go pretty deep. So I just want to go ahead and expose you guys to these the definitions of these ideas, of these concepts, chemical equilibrium, and acids and bases. So let's get started with Chapter 18 and chemical equilibrium. Excuse me while I take a little drink of water and get us going at the end of the day. It seems like my my voice is almost gone. Even though I haven't been talking all day long, but it seems to be gone. Okay, so before I give you a definition of chemical equilibrium, what I do want to point out is a thing called a reversible reaction. So as you can see right here, the bullet point is chemical equilibrium. But before we can give a definition for chemical equilibrium, we need to understand what a reversible reaction is. It turns out that reactions can run in what we call the forward reaction and the reverse reaction. And up to this point, we've just been looking at the forward reaction. We haven't talked about the reverse reaction. So let me give you an example of what that is. Let's say that we have hydrogen reacting with oxygen to form water. You guys performed this in a little test tube during a lab second semester. You collected hydrogen in a little test tube, and there was oxygen already in there. You put a little burning wood splint, and for a lot of people, it gave it a little pop. What was happening there is the H2, the hydrogen, was reacting with O2, the oxygen, to form H2O, or water. Right? So the hydrogen and the oxygen were combining to form water. That is the forward reaction. We can write it as H2 plus O2 goes to form H2O. If we balanced it, it would actually be 2H2 plus O2 goes to form 2H2O, but we won't worry about balancing it right now. Just know that hydrogen and oxygen, the elements themselves, are the reactants, and water, the compound, is the product. But who's to say that hydrogen and oxygen just form water? Can it be the other way around? Can't we take water and break it down into its elements? It turns out that we can. We can go ahead and take water and break it down into its elements. What you do is you take a couple of electric wires, one with a positive, the other one with a negative, run it through some water, and you're going to get bubbling at each one of those electrical wires. What you're forming is hydrogen and oxygen gas. The hydrogen and oxygen gases are actually being produced from the water that is being broken down in a decomposition reaction, right? H2 and O2 forming water is a synthesis reaction, which we learned about earlier. H2O breaking up to H2 and O2 is a decomposition reaction. Okay, so if I wrote the equation as H2 plus O2 goes to form H2O, then the H2O forming H2 and O2 is just a reverse reaction. And so in this reaction, we can have the reaction run in both directions. And actually, that's true of many, a great majority of chemical reactions are what we call reversible. And when they're reversible, chemical equilibrium comes into play. So let's give a definition for what chemical equilibrium is. If you look at the second bullet point under the bullet point, so the second one right here is the definition for chemical equilibrium. Chemical equilibrium is a state of balance for a chemical reaction in which the rate of the forward reaction is equal to the rate of the reverse reaction. That is the definition of chemical equilibrium. The state of balance when the rate of the forward reaction is equal to the rate of the reverse reaction. Now you might say rate of the forward or rate of the reverse. Well, we were talking about rate of the forward reactions all in chapter 17 for the last chapter. We just didn't call it the rate of the forward reaction because we didn't know that there was a reverse reaction. So we just called it the reaction rate. Right? But we're going to have the forward reaction going at a certain rate, the reverse reaction going at another rate. And when they're equal, we've hit equilibrium. Because what happens at equilibrium is that if you look at the last bullet point here, it says no net change in the amount of the reactants and products occurs in the chemical system during chemical equilibrium. Notice it says no net change. When we're talking about net change, we're talking about how, well, there might be changes, but when you kind of count and add your dollars and cents that you gave away versus dollars and cents that you gained, kind of everything balances out. Okay. Same thing with the chemical reaction. You're at equilibrium when the amount of reactants that were turned to products is equal to the number of products that were turned to reactants. Okay. Going back to the money analogy, it's like me coming up to you and say, here's $5, now give me $5. And if I give you $5 and you give me $5, then neither of us is getting any richer or any poorer. We're just exchanging money. But it doesn't mean anything stopped. We can be doing this all day. Every hour I give you $5 and then you give me $5 right back. We're basically just kind of canceling each other out. And that's what happens in chemical equilibrium. The reactants start turning into products, but after a while, the products turn back into reactants. Eventually, the amount of reactants turning into products is the same as the amount of products turning into reactants. Okay. Let me show you what I mean by this. Okay. So first off, at this point, this is the point where I have to admit to you, I have to confess that I lied to you. I lied to you a few chapters ago. In chapter 12, when I told you that you would have a certain amount of reactants and those reactants would all turn to products. It turns out that most of the time that doesn't happen. So let's take a look at with this graph right here. Let's take a look at what I said back in chapter 12, and we'll see how it's different now that we're in chapter 18. So this next slide right here has a chemical equation at the top. 2SO2 plus O2 goes to form 2SO3. And remember what this means, because of the coefficients, that two molecules of sulfur dioxide react with one molecule of oxygen gas, and they form two molecules of sulfur trioxide. So what this graph is showing is, I'll say that the y-axis, and I didn't label it, the y-axis is the number of moles of each reactant. So these coefficients are just ratios, right? So we can start with as much SO2 and O2 as we want. It's just going to react in a certain ratio. 2 SO2s for every 1 O2. So if we start off with 10 moles of SO2, and that's what this big bar right here represents, 10 moles of SO2 and 5 moles of O2, we said that for every 2 moles of this that reacted, 1 mole of this would react, right? So 2 moles of SO2 is going to react with 1 mole of O2. So if I go ahead and do this, we can see we just lost 2 moles of SO2 and 1 mole of O2, because we started with 10 moles of SO2 and 5 moles of O2. And we just created 2 moles of SO3. We had none to begin with. And if we keep doing that, taking 2 of the SO2s, 2 moles of SO2 for every 1 mole of the O2, eventually the SO2 and the O2 concentrations are going to drop. And they're going to be turned into SO3, or at least in this case, moles. until finally all the SO2 and O2 are gone and all of it has turned into SO3. Okay, so this is what we said happened in chapter 12. And this would have gotten you, full credit back then. But guess what? It really doesn't work this way. Well, it does work that way, except at some point in time, we get into what's called an equilibrium. The way this occurred, this reaction went to completion all the way to the right. It was an irreversible reaction. And so your reactants all turned into products. All reactants turned into as much product as we could turn it into, like a limiting reactant problem. So let's see what happens with equilibrium and how this ends up happening here. Okay. All right, so before I go in and show you that, let me just go ahead and show you what happens with chemical equilibrium. I've got this graph right here that you'll notice that the title of this is rate of reaction versus time for this chemical equation. So it's a different chemical equation, but I'm illustrating the same idea. So there's H2 plus I2 goes to form 2HI. Okay, so hydrogen and iodine forms hydrogen iodide. On this graph, we have the rate of the reaction on the left side. And you'll recall we can get that rate from those rate laws. R is equal to K times the concentration of H2 times the concentration of I2, or whatever it might be. I don't know what it is here. And so we're going to get an answer right there. There's also a rate for the reverse reaction, HI turning back into H2 and I2. And right at the very beginning, the concentration of the forward reaction is going to be its maximum because the concentrations of H2 and I2 are at their maximum, right? So if we plug in the concentrations of H2 and I2, and if we go back to the next slide, we're going to see that we started off with 1.5 moles per liter of I2 and 1 mole per liter of H2. Those numbers were just used, or those conditions were used randomly, but this could work with any concentrations. So if we plug these numbers into our rate law, we are going to get this rate right here. And the rate of the reverse reaction is 0 because there is no product. So the rate of the reverse reaction would be something like R is equal to K times the concentration of HI, or concentration of HI squared, whatever power it might be to. And you guys learned last chapter how to figure that out. But when your concentration of HI is 0, then your rate is 0. It doesn't matter to what order it is. All right. So as the reaction takes place, our concentration of H2 and I2 drops, right? Because H2 and I2 are turned into HI. So their concentration is going to drop. And so this number is going to drop. And as the concentration gets smaller and smaller, so does the rate, at least of the forward reaction. The reverse reaction is going the other direction. It may not be going up. In this case, it might not be going too fast. But as we start making HI, then the reaction starts going in the opposite direction. And it might be going slowly at first because the concentration is so small. So it starts going up and up and up. Eventually, there's going to be a point, and it's not necessarily right in between. It could be closer to 0. It could be closer to the initial concentration of the forward rate. We don't know. It really depends on the nature of the reaction. But eventually, those two lines are going to meet somewhere. So here, if you look on the x-axis, the time is measured in hours. After 4 hours of this reaction, the two rates meet. And as they meet, they're going to stay the same, because your concentrations of H2, I2, and HR are not going to change anymore. When the rate of the forward reaction is equal to the rate of the reverse reaction, the moles of HI that reacted are going to be equal to the moles of HI that got formed. I think I said that backwards. Okay. But that works. The moles of H2 that reacted are going to equal to the moles of H2 that got formed from the reverse reaction. Et cetera, and so on. So that's what this next slide shows. So we start off with a certain amount of I2. This magenta line right here is your I2. This dark blue line here is your H2. And the yellow line that jumps out at you here is your HI. It's your product, right? So once again, here's the chemical equation. This graph shows you the concentration of each substance versus time. So as opposed to the last graph that showed you reaction rate on the y-axis, this one's concentration. And so we start off with different amounts of reactants of each reactant, and we start off with no product. Eventually, the product started forming, and as the product starts forming, a reverse reaction is possible, because now this HIs can be turned back into H2 and I2. So here we see them going down. They see H2 and I2 are going down, and the HI is going up. And eventually, it'll flatten out. And when we hit 4 hours and equilibrium is struck, you'll recall that after 4 hours, our rate of the forward and backward reactions were equal to each other. Then after 4 hours, the concentrations of each substance now flattened out, and they don't change. Okay, and that's when you hit equilibrium. So one thing you'll notice is that in the definition of equilibrium is established when the rates of the forward and the backward or reverse reactions are equal to each other, not when the concentrations. These are concentrations, and they're not the same. They are constant. They've stayed constant. They've stabilized, but they are not the same. Okay, just to point it out. We made a whole lot of HI. You'll recall that the rate of the reverse reaction was pretty low, even with all this concentration. So that key is pretty small. The reverse reaction is probably a very slow reaction, much slower than the forward reaction. That's why this reaction works out in this case. Okay. So let's take a look at the other equation that I showed you. So really what we can see in a graph like this is that we can start like we had it with 10 moles of SO2 and 5 moles of O2. How does this equation react differently now that we've learned about chemical equilibrium than earlier? Now, like I said, I confess that I lied to you, but I didn't do it. I did do it on purpose, but I only did it to simplify stuff back in chapter 12. The reality is a little more complex, and now we can go ahead and get into the complexity. Okay, so once again, we start off with 10 moles of SO2 like we did before, and 5 moles of O2. And just to remind you what we did earlier, all right, the 10 moles of SO2 reacted with 5 moles of O2, and they all turned into SO3, and eventually all the SO2 and O2 was used up and turned into SO3. That's what we taught you in chapter 12. That's not really what happens. What happens is more like this. So the SO2 and O2 are still reacting in the same ratios, coefficient ratios, 2 to 1. So 2 moles of the SO2 here react with 1 mole of the O2 to form 2 moles of SO3. Then another 2 moles of SO2 react with another mole of O2 to form 2 more moles of SO3. Now we got 4 moles of SO3, and it keeps happening up to a certain point, whatever that equilibrium might be. In this case, this is the equilibrium. At this point in time, I can keep hitting my space bar to get to the next slide, and nothing else happens. Because at this point, we've established equilibrium. Did the chemical reaction stop? No, it didn't stop. Equilibrium is a dynamic process where the reaction's going on. But at this point in time, the 2 moles that are supposed to be turned into SO3 of SO2 now are being replaced by 2 moles of SO3 turning back into SO2. So what we're seeing here is the net gain of this next time frame, the next minute, the next hour, whatever it takes. We're seeing that 2 moles of this turn into this, but 2 moles of this turn back into this. So really there was no net difference. It's that $5 I give you, and then you give me those $5 back. We've established equilibrium. Right before here, it could have been that, this is 2 moles of this and 1 mole of this react to form 2 more moles of that, just like it did earlier. But as you go further along, it probably takes longer in order for that to happen. But eventually it happens. Until at this point right now, the rate of the forward reaction, these 2 things turning into this, is equal to the rate of the reverse reaction, this thing turning back into this. And that's when we established equilibrium. And we say here that we established equilibrium from the left. We took the reactants on the left of the equation and turned them into products. And then we hit equilibrium from the left, turning into the right. You can even establish equilibrium from the opposite side. Let's say I just give you a container of just SO3, sulfur trioxide gas. All right. So that sulfur trioxide gas is not going to just stay there. This is a reversible reaction, which means that this reaction is going to turn SO3 back into SO2 and O2. And so it does so according to the same coefficients, right? You're still going to make 2 moles of SO2 for every mole of O2 because of the coefficients here. And you're going to lose 2 moles of here, and you'll keep going. But you will notice that now we've already established equilibrium much quicker from the right in this case. Because, it's the nature of the reaction of where this equilibrium is established. You'll recall that these are the heights of each bar that we had earlier when we established equilibrium from the left. I'll do that again. Go ahead and go back to that. So we hit equilibrium from the left. Equilibrium finally occurred here, right? You'll notice there's 4 moles of SO2, 2 moles of O2, and 6 moles of SO3 when we hit equilibrium. Now, when we established it from the right, the reaction went in the opposite direction, but we eventually hit the same equilibrium point. 4 moles of SO2, 2 moles of O2, and 6 moles of SO3. Okay, and so whether you hit equilibrium from the left or the right, it's still going to be the same equilibrium point. It's still going to give you the same relative amounts of products to reactants. Okay, your products here to reactants here. And that's how you can tell you've hit equilibrium, or how you can even predict when you will hit equilibrium. Excuse me. I'm just getting a little more water. How would we know when equilibrium is established? Well, let's take a look at this here. Okay. This next table, and this is a table from page 567 of your book, shows you 3 experiments done for this equilibrium system with H2, I2, and 2HI. These are the ones that I showed you earlier with the graphs. And what happens at equilibrium? So they did 3 experiments. And here we had trial 1, or experiment 1, 2, and 3. And in each case, they start off with a different amount of reactants and products. In the first case, they start off with 1 mole per liter of H2, 2 moles per liter of I2, and no HI. So they just added reactants. The second case, they hit equilibrium from the right. No H2, no I2, 5 moles per liter of HI. And the third case, they put a little bit of all. 1 mole per liter of H2, 1 mole per liter of I2, and 1 mole per liter of HI. And they let the chemical reactions, let's say imagine these 3 different containers. And they let the reactants go ahead and take place until equilibrium was established. Then once the chemical reactions hit equilibrium, each of these experiments hit equilibrium, then they just measured the concentrations. What were they? Well, they were this. You'll notice that in each case, they're all different. 0.06587 for H2 in the first experiment, 1.0659 moles per liter of I2, and 1.8682 moles per liter of HI. All these were the first experiment. The second experiment had 0.5525 for H2, 0.5525 for I2, and 3.8950 for HI. And the third one had 0.2485 concentration of H2, 0.2485 concentration of I2, and 1.7518 concentration of HI. Okay. Now these numbers look like they're all over the place, right? These are the concentrations once we hit equilibrium. These 3 columns were what you start off with, and these concentrations turned into these concentrations at equilibrium. See how each of these subscripts have EQ on them? So those are the concentrations at equilibrium. This 0 means a time 0 at the beginning. One thing they had in common was this. If you went ahead and took the concentration of HI for each experiment, took the concentration of HI and you squared it, divided by the concentration of H2 times the concentration of I2, you got the same ratio of HI squared to H2 times I2. If you took HI and then plugged it in, squared it, right there, multiplied it by H2 times I2, right here and right here, you got 49.70. If you did the same thing for the second one, the second experiment, 3.8950, and squared it, right here, divided by 0.5525 times 0.5525, You got 49.70. The third one, same thing. You took this concentration here, 1.7515, squared it, divided by 0.2485 times 0.2485. You got 49.70. Wow, is that a coincidence? Is that magic? No. That's how we establish equilibrium. This ratio here for this equation is what we call the equilibrium constant. Actually, this whole equation is called the expression for the equilibrium constant. And the number that we get when we plug these values in is the equilibrium constant. Notice that it's constant in there because you always get the same number, at least at a specific temperature. If you change the temperature, the equilibrium constant actually changes. So what is this equilibrium constant and how can we calculate it? Is there an equation? And the answer to that is yes, there is. Now, your book calls this the expression for equilibrium constant. I'm going to show you how you can, first off, come up with the equation. That's what we're going to be doing in a lot of the homework for today. You're going to come up with an equation to calculate the equilibrium constant. Then you're actually going to calculate the equilibrium constant. The equilibrium constant is a number. Really, it's a ratio. It's a ratio of products to reactants at equilibrium. So that once a chemical equation is at equilibrium, it has a certain ratio of products to reactants. How do you get that? By coming up with the expression for the equilibrium constant, also known as the law of mass action. I use this term a lot because a lot of books use this term, the law of mass action. Law of mass action is the equation for the equilibrium constant or the equilibrium constant expression. Your book uses that term, equilibrium constant expression. So, like I said, we're going to do two things here. We're going to learn how to come up with the expression for the equilibrium constant, also known as the law of mass action, which I might call, just out of sheer kind of, that's just kind of something I've learned. And so out of familiarity, I call it that. Hopefully it's not too confusing. So how we come up with the equation, then how we calculate the number. Okay. So let's go ahead and do this. You'll notice that for any reaction, and what I have here is a hypothetical reaction. This hypothetical reaction has reactants A and B and products C and D. You'll notice that this is not the equilibrium arrows that I showed you earlier. Microsoft Word didn't have, or PowerPoint, Microsoft didn't have the nice actual equilibrium arrows that we saw earlier. But so this will make do. These are reactants. This product, this says that this reaction is an a reversible reaction. So A, B turn into C and D, and C and D can turn back into A and B. These little lowercase letters in front, M, N, P, and Q, those are the coefficients, okay? And the reason I put those up there is because they are part of the equilibrium constant expression. So when you make your equilibrium constant expression, you always start off with K equals 2. Always K equals 2. K, big capital K stands for the equilibrium constant. So my equilibrium constant is equal to, and then you put the concentration of each product in the numerator. So here our products were C and D. So I'm going to put, remember that we use these brackets last chapter to represent the concentration of a substance. So brackets around C basically says concentration of substance C to the power of P, that's its coefficient, times the concentration of substance D. Notice it's times and not plus. Since there's a plus in the chemical equation, people use plus a lot. I see this all the time in this equilibrium expression. But it's not plus, it's times. So times the concentration of D to the Q. Right? So basically you take each product, get their concentration, and then raise each one of them to the power of their coefficient respectively. C to the P times D to the Q. Divided by the concentration of the reactants, each one to their coefficient. So concentration of A to the M times the concentration of B to the N. This would be the equilibrium expression for this equation. Every equation is a little different, right? There's different reactants, there's different products. You just plug in the correct formulas in each one of these. Sometimes there's 2 reactants and 3 products. Sometimes there's 2 reactants and 1 product. Sometimes there's 3 reactants and 2 products. Sometimes there's 3 reactants and 1 product, 1 reactant and 2 products, whatever it might be. For each product, you put a term in the numerator. For each reactant, you put a term in the denominator. Okay. So that's how you write the equation or the expression of the equilibrium constant. How do you get the equilibrium constant? Well, now you find the concentrations at equilibrium. If you can figure out the concentrations at equilibrium at any equilibrium point, you plug them in, and that'll give you the equilibrium constant. And that temperature should have just one equilibrium constant. Okay. All right, so let's do some sample problems. Your homework is going to be doing these things. So let's do some sample problems. All right, so the first thing we're going to do is this thing says determining the law of mass action. So we're going to determine really the equilibrium expression. What's the equation you're going to use? So let's do a sample problem here where we find out the equilibrium expression or law of mass action for each one of these 5 equilibrium products. One thing to point out is that you only include a substance in the equilibrium expression if it's a gas or if it's aqueous, AQ. You do not for solids and liquids. And there's a big old chemical reason, statistical reason why. And I really don't want to go into it. And you probably don't want to have me go over it and talk about chemical activities for different states of matter. Just suffice it to say, gases and aqueous substances, you can use their concentrations. And for solids and liquids, you plug in a big 1 in there, or basically just ignore them. Okay. So let's try these sample problems. Okay, for this first problem, it's really like 5 problems in one, but they're not really that hard as long as you can kind of see the pattern. So hopefully you can see this. Let me go ahead and do this. If I start doing this, it starts my cursor. All right, so determine the law of mass action for these 5 different equations. So let's go do that. We might have to move some stuff around, but let's do that. So the first one is N2 plus O2 goes to form 2NO. Remember that it is products on top, reactants on the bottom. So you always start these equations with K equals 2. And then you put the concentration of each product on top. So this first one is NO, and NO, and you put it in brackets, this concentration. And notice that the coefficient here is a 2, so you square it. Whatever the concentration of NO is, you square it, and that's your numerator for this. Then you divide by the concentration of the reactants. There's 2 of them, N2 and O2. So you do a bracket for N2 and a bracket for O2. All righty. And there you go. There is your law of mass action right there. That's your equilibrium expression for this equation right here. So we did that one. And you just plug in the equilibrium concentrations. That gets your equilibrium constant. Let's do the next one. N2O4 gas breaks up into 2NO2 gas. So this one, put a line right here, different one. K equals 2. Product is NO, 2, and we get the concentration. And since the coefficient is 2, we square it. That's squared. Divided by the concentration of the reactant, N2O4. That's a 4. Sorry. No coefficient, so we leave it to the first, just like we did with these guys over here. Okay, and so that's that one. For this one right here, there's 2 reactants and 2 products. So K equals 2. It's 2 products are SiCl4. All right, so it takes me a little longer, this thing. And H2 has a coefficient of 2, so we square it. Divided by the reactants, SiH4. And once again, don't forget that the brackets represent concentration of times concentration of Cl2. And that one gets squared. Okay. So that's this one. This next one, let me go ahead and move that around here so you can see that they're all different ones. This next one, same idea. Everything's got a coefficient in this one, right? So 2 reactants, 2 products. K equals to concentration of PCl3. And we squared that one because of the 2 right here. And concentration of Br2. And that one's got a coefficient of 3. So we cube it. Divided by the 2 reactants are PBr3 and Cl2. So PBr3 squared and Cl2. That's a 2 to the cubed. Okay. Once again, the coefficients, the subscript, the exponents are the coefficients there. And the last one is, let's see, we did just that, did this one. This one is heterogeneous, which means that there's solids or liquids in there, and we're going to ignore those. We don't technically ignore them. We put a 1 in for them. And if you want me to kind of do the whole thing, it looks like this. K equals to AL C. Oh no, actually, let me go ahead and undo those. Since it is AlCl3 is a solid, we plug in a 1 for it. 1 times the concentration of F2 squared divided by AlF3 is also a solid, so we plug in a 1. Cl2 is a gas. And once again, the coefficient of Cl2 is a 3. Ooh, I messed up. So this should be cubed, and so should this. Well, let me do this. Go ahead. There's everything here. And there we go. And if I just ignore these guys, so one thing to point out is that this right here and this right here, they're 1s because these guys are solids. And since they're solids or liquids, we would put a 1 in there. We wouldn't put concentration of. The concentration of them is 1. So basically, what you can do is you can just ignore them. If I were to rewrite this out, basically it's K equals to the concentration of F2 to the 3rd power divided by the concentration of, what happened there? I'm having a hard time writing down here. Let me move this up here because apparently the program's not letting me write there. And finish off my problem. Concentration of Cl2 to the 3rd power. Okay, so these two are the same thing, just with the 1s right there. So I would go ahead and ask you just to write this. You don't have to plug the 1s in. Okay, so these are the equilibrium expressions for each of these 5 reactions right here. Right? N2 plus O2 go from 2 and O. That's this one right here. N2O4 goes to 2NO2. That's this one right here. This one here is right here. This equation's law of mass action or equilibrium expression is right here. And this one right here is down there. Okay. Okay. So the next one here asks you to calculate the equilibrium constant for the following reaction. And you got N2O4 breaking down into two NO2s. And you've got some equilibrium concentrations down here. So now we can go ahead and just come up with our equation. It was we already came up with the equation earlier, sample problem. Let's take that equation and plug these numbers in and see what our equilibrium constant is. Okay, so for this problem right here, it says calculate, hopefully you can read this up, calculate the equilibrium constant K for the following reaction. You got N2O4 goes to 2NO2. This is one of the sample problems we did earlier. So let's go ahead and figure out, first off, the equation we'd use. For the equilibrium constant, it's K equals to, oops, let me go ahead and click on the pen. K equals to products, concentration NO2. Right, concentration NO2 is the product. Square it because of the coefficient. Right. And then divide by N2O4. So there is my equilibrium expression, also known as law of mass action. Now what I have to do is I have to actually calculate the K. We're actually calculating the K this time. And we're given these numbers right here. These are the concentrations at equilibrium. If these concentrations are not the equilibrium concentrations, then you can't do this. But we're assuming that they are. So K is going to equal to NO2 concentration 0.35. So I'm going to plug in as 0.35. And, you know, notice that we need here to take the concentration of NO2 and square it. And then divide by concentration of N2O4, which is 0.023, 0.023. Plug it in. You'll notice that I'm not using units here. Usually I tell you to use units. But for equilibrium, we use a thing called activities, which don't have units because the units cancel out. And as I mentioned, I'm not going to get into what activities are. It gets a little complicated, so we're not going to worry about it. Just to point out, this thing here looks like a really messy decimal, but it's a decimal. Okay. So let's go ahead and calculate this out. I'm using my calculator now to calculate 0.35 squared, which is actually 0.111225, divided by 0.023, and I get 5.33. So my answer to this problem here is 5.33. This number is your equilibrium constant for this reaction. That means that equilibrium, whatever the concentration of NO2 squared is, should be 5.33 times bigger than whatever this is. It doesn't have to be these numbers, but as long as the concentration of your NO2 squared, once you take that and square it, if it's 5.33 times bigger than this, then you're at equilibrium. Okay. Okay, so the last one. This one says calculate the equilibrium constant K for the following reaction. Oh wait, no, I'm sorry. This is not the last one. It's the second to the last one. So we got this chemical equation. We already figured out the equilibrium constant expression for it, the law of mass action. Let's take that and plug in these numbers here into the equation and figure out the answer. Okay, so this problem is kind of like the last one over here. Once again, let me go ahead and get my pen going here and my cursor. If I do that, it starts off the cursor. All right, so we got this chemical equation, 2PBr3 plus 3Cl2 goes to form 2PCl3 plus 3Br2. And we were supposed to calculate the equilibrium constant, the K, when these are the concentrations. So we already saw from this earlier sample problem that, your equation that you're going to use is K equals to, once again, you just take products first. PCl3 coefficient is 2, so we square it. Times Br2 is the other product. Concentration of, coefficient is 3, so we cube it. And then that's your numerator, right? The numerator. Denominator is these guys over here, PBr3. PBr3. And once again, the coefficient is 2, so we square it. And Cl2 is your other reactant. Oh, that was ugly. And since Cl2's coefficient is a 3, we cube it. All right, so that's my law of mass action. We saw it in an earlier sample problem. Now we just plug in these numbers into here. K is going to be equal to, let's see, what's PCl3? That's this one right here, right? 0.65. And we're going to square that. Don't ask me why scientists like to replace brackets with parentheses when they plug numbers in, but we tend to do that. Br2 is 0.585. And that one's going to be cubed to the third power. PBr3's is 0.0045. 0.0045. And that one's going to be squared. And Cl2's concentration right here is 0.023 to the third. After all these weeks, I still haven't gotten that much better writing on this thing, but there we go. All right, so that's going to equal to, so let me get my calculator out. This is calculator time now. 0.65 squared times 0.585 cubed. You gotta know how your calculator cubes and squares. Divided by 0.0045 squared. And then divided again by 0.023 to the third power, or cubed. And that's going to give me a big number, which is 3.43 times 10 to the, let's see, 3, 6, 7, 8. 3.43 times 10 to the 8th. Sometimes these K's will be really big. This one's not really that big. 3.43 times 10 to the 8th, which basically is like 343 million. And that's your equilibrium constant for this reaction at this temperature. Okay. And a chemical, this chemical reaction, a chemical system with this chemical reaction going does not have to have these concentrations to be at equilibrium, as long as concentration of PCl3 squared times Br2 cubed is 3.43 times 10 to the 8th times larger than PBr3 squared times Cl2 cubed. Okay, and that's basically what an equilibrium constant is telling you. Wherever you start off from, whenever you start off with all reactant and zero product, you're starting off at 0. And as the reaction moves to the right, your products over reactants is going to start growing and growing and growing. You would be, if it was all products and no reactants, then you would be at infinity, which really doesn't exist, but that's kind of what you get when you're dividing by 0. So this should be somewhere before all the products turn to reactants. We say, in this case, with K so much very large, a K that is larger than 1, actually usually is much larger than 1, means that the equilibrium favors the products. Because at equilibrium, you're going to have much more products than reactants. And even though it doesn't seem like 0.65 and 0.585 is so much bigger, it's much bigger than 0.0045 and 0.0023. Okay. When the equilibrium constant is much smaller than 1, right? Not just one smaller than 1, much smaller, then it favors the reactants. Reactants are favored. Okay. All right, this last one throws you a little bit of a curveball. It's a little different. This one, instead of asking you for the equilibrium constant, which you would need the equilibrium constant expression for, it asks you to calculate the concentration of F2 for the following reaction. So here's your reaction. F2 is right over here. And so we want to calculate the F2 reaction. One thing to point out, this is one of those heterogeneous equilibria. When you do your sample problems or your homework problems, they're going to ask you for some heterogeneous equilibria, equilibrium expressions. What is a heterogeneous equilibrium? Well, when a chemical reaction has a solid or liquid in it, really heterogeneous when they're not all gases or all aqueous, but really it's mostly has an effect when there's solids or liquids in there. So here we have a couple solids. And remember, when you have solids, their activity is 1. And since that's what we're really putting into equilibrium constants, really you just ignore them. You plug in a 1 for them, and 1 times whatever gives you whatever you had there to begin with. So we'll do the sample problem right now using that. And here they tell you your concentration of chlorine at equilibrium is 0.884, and they give you the equilibrium constant. They give you the K. So let's see how we would calculate the F, fluorine concentration. So in this last problem, they want us to calculate F2. They don't want us to calculate the equilibrium constant. We already have the equilibrium constant. It's right there. Makeshift arrow I have there. So we don't want to find equilibrium constant. We want to find F2. And that's because as part of the equation, F2 is one of the substances. So let's go ahead and do this problem. If you'll notice, we did the law of mass action earlier for this. We can do it again. Once again, you'll notice that there is a solid here and a solid here. And solids and liquids we do not include in our law of mass action. We ignore them. We plug in 1s for them. And when you multiply 1 by anything, it's the same thing. All right. So law of mass action for this is K equals 2. Well, there's F2 is our only product that we're going to be using here. Concentration of F2, which is what I'm looking for anyway. And I wanted to cube that. And once again, this is a solid, so we don't include it. That's it. That's all that goes in our numerator. In our denominator, once again, the AlF3, we don't include it. We didn't include AlCl3 either. Cl2 is in the denominator, and that also has a cube to it. Right? The coefficient here is a 3, just like it was over here. So we're going to go ahead and cube that. So that's our law of mass action for this equation. That's our equilibrium expression. I'm sorry, I keep using those back and forth because they're interchangeable. At least in my mind, they are. All right, so we're being asked to find F2. Before, we've been given the concentrations of all the substances solved for K. This time we're being given K. So I'm going to plug that in. So I guess I'll put it right here. 0.025 is our K, and that's going to equal to the concentration of F2. It's going to be cubed divided by the concentration of Cl2. And Cl2 we're also given is 0.884. 0.884 to the third. All right, so before I go ahead and do all the calculations, I'm going to move stuff around first so it doesn't become a mess. Right? So in order to get F2 by itself, I need to multiply both sides by 0.884 cubed. so that they cancel on the right. And I need to multiply the left by 0.884 cubed. And if I go ahead and rearrange that, swap sides, I get that F2 concentration cubed is equal to 0.884 to the third times a concentration of 0.025, which is my equilibrium constant. Now, since I just want F, not the cube of F, I go ahead and take the third root, which you can find on your calculator, hopefully. Or maybe it's to the power of a third also. When you do that now, you get your concentration of F2 by itself equals 2, and here I'm going to my calculator, and in my calculator I get 0.884 to the third power, gives me 0.6908, something like that, times 0.025, gives me 0.01727, and if I take the third root, let's see, on my calculator, where is my third root? The hardest part is the fact that I'm having a hard time seeing here. Okay, and so now that we found our third root button, I guess I could have also done x to the 0.333 or 1/3. But when I get my third root, I end up with 0.258. So my answer here is 0.258, and then we're being molars. Okay, and there is your answer. So this time we actually solved for a concentration. Could have been Cl2, but that would have been even hairier. Well, let me go ahead and do that. I like to do this in different colors. We solved for that, and for that you have to multiply the Cl2, and it was cubed, and we have to move it to the side. I could have cubed it first and then moved it, but I figured I'd wait till later. And then just took the third root. Okay, so that's how you do the problem like that. All right, I hope this has been helpful. I know it's a whole lot to digest. Let me go back to the slide over here to end here. I know it's a whole lot to digest, and chemical equilibrium is really important concept in chemistry, because if things went to a completion, if all reactions went all the way from reactants to products all the time, then there wouldn't be as many chemical reactions as there are, because almost half of the chemical reactions are the reverse reactions. There wouldn't be reversible reactions. We'd have to figure out which direction reactions went, and then we wouldn't be able to reverse them. But also the effects are different. I mean, if you're expecting to get a certain amount of product, how much are you actually going to get? How much product is actually going to be made? That's an important question. But also the effects. Some acids are strong acids because they're basically effectively go to completion, and we'll see that in the next chapter. Some are what we call weak acids, like acetic acid, that, it's not going to burn your face, even though it will, you don't want to drop any acetic acid on you, which is vinegar, which is the acid in vinegar. But we find it relatively safe, although careful with, getting some of that stuff in your eye. You have to wash it out, and it's going to sting. But it's because it has an equilibrium and an equilibrium constant that doesn't kind of turn all the acid molecules into what they'll turn into, which we'll talk about next chapter. And so therefore it makes it a weak acid versus a strong acid. Okay. So until next time, I hope this was helpful. And I hope that you at least kind of got an idea of what chemical equilibrium is, or at least the law of mass action is. For the next section, we'll talk about how chemical equilibrium can be affected in Le Chatelier's principle. All right. Have a good evening.